Right, so we're working on 8.5, where we test means from 2 paired samples. As I said, the easiest way to compare means is when the samples are paired, and we've got our definition here. Paired samples, where every value in the first sample is paired with exactly 1 value in the second sample. Okay. The advantage of using matched pairs is that confounding variables are controlled when these are the same people. So let's just say many confounding variables. When both groups involve the same people. And if they do involve the same people, then they're matched pairs. Remember, confounding variables, that happens when you say, oh, one group, they were better educated, so it makes sense that they're going to have better health. Well, if it's the same people in each group, you can't argue that one group is better educated. So the confounding variable, which would be their education level, I don't know if they did better because of the medicine or because of their education level. That confounding variable vanishes when both groups are the same group. Okay, any questions about that? Disadvantage of using matched pair samples is, I would just say, many studies can't use the same people for a control and treatment. Okay. Yeah, I mean, it doesn't take much imagination. So if you're gonna do something about looking at how coffee affects someone's health, you can't give someone 1 cup of coffee. They have to drink it for years, and so you'd have to track a random group that is told to drink coffee, and another random group that's told to not drink coffee. Those can't be the same people if it's going to take years to follow them. So that's the idea. It's just, it doesn't work in many cases. But you'll see here, in studies where you test people before and after a treatment, that works really well. So let's do it this way. Under matched pair samples, I want to add another note here and just say these tend to be the same subjects with the same measurements taken under 2 different conditions. Okay, so just as a, in parentheses, I'll say before / after treatment. Okay, so those before-after tests are a great way for doing matched pair. Then here comes the example. So it says Prozac is a drug which is meant to elevate the moods of people who are depressed. In the following sample, mood levels, whatever that is, were recorded before and after taking Prozac. Higher scores are good. They mean less depressed psychological states. We label before Prozac as X and after Prozac as Y. We're supposed to test the claim at 1% significance that Prozac is effective in elevating mood on average. Okay, so there's an assumption we'll have to make because the samples are small. We're going to have to make an assumption about normality, and I'll do that when we get to it. Okay, so it says we're not directly interested in the before or after values here. What do you think we really are interested for each of these individuals? Does it matter that this guy has a 6 here? The gap. Thank you, Matthew. What's really important is seeing the change. So 4 doesn't matter. 10, well, that's a person that went from 4 to a 10, right? That's an increase of 6 points. So we're interested in the change or the differences. I'll say the changes or differences. Differences is a good word because we're going to use D as another variable. And D will stand for difference. Okay, any questions about all that? All right, so next thing we do is a bunch of number crunching. Okay, so let's do a real quick step-by-step. So you have to compute D, which is X minus Y for every pair, okay? Then you have to compute D bar and SD, which are the mean and standard deviation of the Ds. Now, let's do that real quick. So we're subtracting X minus Y. Some of these are negative, okay? So 3 minus 5 is negative 2 is the idea. And then 0 minus 1, 6 minus 5. Oops, that's a positive one, isn't it? So it's positive when the mood goes down. Okay, so that's actually a bad thing. 0 means that no change at all. 4 minus 10 is negative 6. 3 minus 9, negative 6. 2 minus 7, negative 5. 1 minus 11, negative 10. 4 minus 8 is negative 4. Okay, so again, when it's negative, that means the before is lower, the after is higher. So the mood went up when it's negative, and that's a good thing. So the negative ones are the good news. Okay. And the more negative it is, the better. Okay. Any questions? Okay, now, so you're actually going to do a hypothesis test on the differences. And so remember, we always need a mean and a standard deviation. So I'm going to go back here and say, right next to the problem, let's assume the population of differences D, which is x minus y, is approximately normal. Okay, and that's a requirement if your sample sizes are less than 30. So any questions here? So technically speaking, I need to tell you when the sample sizes are small, I need to tell you that the differences are normal. The solution to that weird situation is the sample sizes probably should be bigger than 30. But it's in our book, most of these are small sample sizes just because it's so much work to do large sample sizes. You have to do all these computations on this one. Okay, so here you will check N is bigger than 30 or the population of D's is normal. Okay. So let's go ahead and get our mean. So the D bar, it will be X bar on the calculator because the calculator doesn't know what D is. So just real quick, would you be willing to key those in to your calculator? I'll just go through it. We've done this lots of times, so I'm not going to go through steps. So I'm doing an on clear and then data, and then I have to type in all the D's. So excuse me while I go to that. Don't forget the negative button is below the 3. It's not the subtraction button. Okay, so I've got mine all keyed in here. And then, so once you've got them all keyed in, you press clear, second data, one variable stats, and then just remember that X bar is really our D bar, and SX is really SD. Okay, and N is 9. So those are the numbers we needed. I'll say negative 3.67, I think, for D bar. SD is 3.5 exactly, which is weird. N is 9. Okay, any questions? The 9 is too small. This is less than 30. So too small. But the population of differences is normal. Okay, so that's that first step. So once you get this part done, there's a null hypothesis and an alternative hypothesis. Just a quick notation, mu1 is going to be the mean of x's. Mu2, everybody's favorite Pokemon, at least I hope, is the mean of the y's. Everybody knows mu2 is way better than mu1. Mu-d is mu1 minus mu2. So that's the mean difference. Charizard? Charizard was the best Pokemon. I don't know. Does he have a Greek letter named after him? Okay. It's pretty straightforward. Okay, so, and then when we do the null hypothesis, it's always going to be mu1 equals mu2, which is totally false if you're into Pokemon. And then the alternative hypothesis, well, let's think about this. So mu1 is the before mean. So these are the mood levels before. And mu2 obviously is the mood level after. And I'm frozen. Oh, here we go. So if the medication's working, is it mu1 less or greater than mu2? And by the way, I think that we're supposed to test the claim that what's it called again? It sounds over X. What's it called again? Prozac. That Prozac's effective in elevating mood. So that is, yeah, right, Andrea. The mood before would be less than the mood after if Prozac is working. Okay, and that would be on average. Everybody's gonna be a little different. Okay, now is there any question about that? This is gonna be a left tail test. Now, don't forget that the mean difference is mu1 minus mu2. So if mu1 is equal to mu2, the null hypothesis translates into the statement that the mean difference would be 0, okay? If mu1 is equal to mu2, then the difference is 0. So on average, what that says is on average, there's no difference before and after Prozac. All right, any questions about that? Now let's pinch. I'm gonna go back and copy that test statistic. So this is the statistic we used in the last hypothesis test, and because we're still working with means, it's the same test statistic. So I'm just gonna copy that and paste it to this lesson. We're basically doing the same hypothesis test. Okay. That's your test statistic. TS is how we abbreviate test stat. And you're just counting how many standard errors the mean is from the assumed population mean. There's a little difference here. Okay, X bar should be D bar, so let's figure that out. This is the mean of sample differences. And then the mu here should be the mean of differences in the population. So that's mu with a D subscript. And then, of course, we're doing a test on the differences. So you want the standard deviation of the differences down here. This is the same computation. It's really the same formula. We're just, you know, updating with the correct notation. So we can do this right now. So the D bar was negative 3.67. Okay, minus the mean difference, that's a hypothetical value. Notice what we're assuming it is. The mean difference is 0, and this will always be the case. Okay, so you'll always have a 0 for that. Whenever we test differences, the null hypothesis is there's no difference. between two populations on average. So if the null hypothesis says no difference, then the mean difference is 0. And you'll see that in 2 more hypothesis tests that are coming up. Anyway, the standard deviation was 3.5. And that's over the square root of n, which was 9. Okay, so if anybody could post what that is, that would be awesome. Correct, negative 3.14, I'm going to say 6 here. Okay, any questions? Okay, so once you have your test statistic, this tells you again that the mean difference is a little more than 3 standard errors from no difference. So again, d bar is the observed difference, and mu d is the assumption that there was no change at all on average. So we're more than 3 standard deviations away from no difference, which means it seems like it's a pretty good difference. Okay, any questions? So with this group, we've got significant change, statistically significant. Okay, any questions? Okay, now, so the question is always, is that statistically significant? And statistical significance is measured in 2 ways, and they're equivalent. But I want you to know how to do it both ways. So the p-value and the critical value both are sort of redundant. Okay, so the critical value tells you what statistical significance requires in terms of the number of standard errors. So this is a left tail test, and let's make a note back here. Yeah, we said it already. It's already a left tail test. With a left tail test, you mark off a critical value. It's going to be negative because it's a left tail test. Okay, and the area of the tail here is our alpha value. So I don't remember what alpha was. It says 1% significance, and so the level of significance is alpha. Okay, so let's go ahead and we'll mark the area of that tail as alpha, 0.01. Okay, any questions? We have to look up the critical value, and this will tell us, what's required for statistical significance. So on table A2, it's a one-tail test, so you have to find a 0.01 alpha, but make sure it's the one-tail heading. Okay, now the degrees of freedom are always n-1. Well, I said always. For now, the degrees of freedom are n-1. Of course, 9 minus 1 this time is going to be 8. Okay? So this is how you find the t-distribution critical value. Okay, any questions? Okay, so let me grab that real quick. Table A2. All right, so okay, that's better. All right, so we had 8 degrees of freedom here, and a one tail with a 0.01 alpha. So this is where we're going, just like this. So that's actually a lot of standard errors for statistical significance. Make sure I'm doing it right here. 8 degrees of freedom, 0.01, one tail, got it. So this thing is telling us that you're going to have to go 2.896 standard errors to be considered statistically significant. Okay, any questions about the table? Okay, 2.896 is what it said. Oops. Okay, so then it's your job, okay, we've just said, okay, 2.896 standard errors is significant, but because it's a left tail test, that means the t-square needs to be a negative 2.896. Okay, this is a left tail test. The critical values on the left are negative. Just like our test statistic was negative up here. Okay. And notice our test statistic's negative 3.146, which is just to the left of the negative 2.896. So I'm going to put right here. This guy is our test statistic. And when it falls into one of these tails, that means it's statistically significant when you use a 1% level of significance. That just means that with the null hypothesis being true, if the null hypothesis is true, then there's less than a 1% chance of getting a value out as low as we got. So this is just one way of measuring statistical significance. Okay, any questions about that one? Why n minus 1? Matthew, it has to do, the t-distribution arises when you use a sample standard deviation, and sample standard deviations vary randomly. And that variability in a sample standard deviation, I'm just looking at this formula right here, the variability in the standard deviation in the denominator is the amount of variability depends on the degrees of freedom in the standard deviation. And you may remember that the deviations in a standard deviation always add up to 0. So if there are 9 deviations from the mean in the standard deviation, when you add up those 9, they add up to 0, which is to say that the last one's not random. Only 8 of the only 8 of the 9 deviations are random deviations, and degrees of freedom is a measure of how random the standard deviation is, because the randomness in the standard deviation is what determines the width of the distribution. There are 9 deviations, but only 8 random values. That's why we use n minus 1 for degrees of freedom. Is that okay, Matthew? Kind of complicated. Okay. So there we go. Next thing is the p-value. So the p-value is just a different way of determining statistical significance. We've already decided that our test statistic is significant. Let me make this note here. This is significant since it's in the left tail. Remember, this is a left tail test. So again, this is one way of determining significance. But there's another way called p-value. So the p-value is the probability of getting something that far into the left tail. So we know it's less than 1% because it's in the 1% region here. But it's less than 1%, but what is it? Well, I'm just going to draw that picture again. Actually, I almost want to just copy it. That feels like cheating. But, you know, I can cheat. It's okay. You can't cheat, but I can. Okay, so let's put in that 2.896 here. No. That's not what it was. The test statistic is negative 3.146. So I'm going to put it a little further into the tail. So that's the test statistic. Okay, and then the area to the left of that is the probability of getting something at least this low. And that's called a p-value. So how probable was this? Okay. So there's a table A3 for determining this. Is just, it's not great. But let me show you I'll draw it in here real quick. Yeah, I mean, I'm really proud of the table because there aren't many. It's a unique table. So that's like the only thing I've done. Actually, I copied it from somebody else. So not directly, but the idea. Degrees of freedom is still n minus 1. I think the degrees of freedom go horizontally this time. So forgive me while I do degrees of freedom that way. This is table A3. Again, the degrees of freedom are n minus 1. So here that's going to be 8. And then the t statistic you go down to whatever we got. Now I'm going to do negative 3.1, so we have to round the negative 3.146 to one place. This is why it's not great. It's not as precise as it could be, but it's one of those things. It's a table, so you're not going to get great precision from a tool like this. Okay, so that's how that table works. Okay, let's look at it. Mostly I'm fond of the table because of how terrifying it is. So here's the table. I don't know, there's just something evil in me that delights in seeing things like this. I don't like horror movies. You'd think I did. Okay, so I said negative 3.1, I think. So I can see it on here. Don't strain your eyes. Well, maybe do, I don't know. Please don't strain your eyes. Okay, so there's 8 degrees of freedom up on the top, and negative 3.1 is our negative test statistic. I hope I did that right. That look right? So that 0.0073, remember these tables for p-values only give areas to the left, just like table A1, which was the first table we started using. That was for the normal distribution. This is the t distribution, but the table is the same. It gives the area to the left. Okay, so this thing, it looks like it's 0.0073. Okay, with 8 degrees of freedom. So let's see, pop back here, 0.0073. Okay. Now, I just remind you that on two-tailed tests, we double that because you're trying to find the probability of getting something at least as extreme as what you got. We got a negative 3.146, but on a two-tailed test, we'd say, what's the probability of getting that in either direction? Because again, a two-tailed test allows it to go either way. Okay, so, but this is not a two-tailed test, so we don't have to worry about that here. But I did want to show you something on Canvas that I posted last night. So I put a little, I'm putting p-value calculators on Canvas for you guys. And I made these in a graphing calculator called Desmos. It's pretty good. It's not great, it's pretty good. So I'm going to do a new share and see if I can get over to Canvas here. I do not have a browser window open. How about that? Half a moment. Okay, let's try it again. Oh yeah, okay. So I'm hoping, just ignore this. What's open right now? That is not what I wanted to share. Okay, so it's on Canvas. In the Math 110H, hopefully first thing you see says p-value calculators. Are you guys seeing this? You're not. Okay, hang on. Okay. I think you're seeing this. Okay, so this is my Canvas page. Sort of looks like yours. I'm hoping the first thing you see when you log in, let's see, what's this student view? Yeah, sort of like that. So the first thing you log in is the p-value calculator page. So if you just click on that, and you have to know the name of the distribution. We've already done the normal, but this one's the t distribution. Oh, there's a chat. Hang on. What's it say? Oh, you saw it earlier. So we're not doing the z normal distribution. We'll do that next again. But whenever we work with means, generally, you have to think about, is it t or z? This one says t, and that's the name of the formula that we computed. So go into the student's t distribution and opens this Desmos calculator. And all you have to do is put in your degrees of freedom here. And I think it was just 8. You see how the distribution changed. I don't know if you saw that. Smaller degrees of freedom, it's like if I put in 3 degrees of freedom, it gets the tails get thicker is what happens. Anyway, I've got 8 degrees of freedom here, and the tails are thinner. Then you have to type in your t statistic, which was negative 3.146. And then what I have it doing is it shows the area of the tail. You can see it's shaded here in the graph, so you can kind of get a picture of what your p-value looks like. It's just a thin little thing. And the A tail, that's the area of the tail. I didn't want to say that was the p-value because you might have to double it if it's a two-tailed test. Okay. Anyway, so the area of the tail is 0.00684, which I've rounded to 0.007. And remember, the table gave a 0.0073. So they're both rounding to 0.007. But this computerized version in Desmos that I'm showing you is more precise because it allowed 3 places after the decimal for the t statistic, where the table only allows 1 place after the decimal. So it's just going to be less precise, but it still leads to the same conclusion. They're both rounding to 0.007. Okay. But I think you could probably argue that this one's easier to use, and I'm happy to agree that you guys can use this. There's also one for the normal distribution, so I'm going to go back to Canvas real quick. There's a normal distribution, but you may remember the normal distribution doesn't have a degree of freedom. So this is basically the same thing. You just put in your test statistic if it's a z distribution test. And if it's negative, it gives you the area of the left tail. If your z-score is positive, it assumes it's a right tail test and gives you the area of the right tail. Okay? But you just type in your value, whatever it is. So if it's 2.64, then the area of the tail is here, and that's the p-value for a 1 tail. Double it for a 2 tail. Okay, so that's Z and T, and then you may have noticed there's some others on there. There's an F, and later on there'll be a chi-square when we get to it. Okay. So let me come back over to my iPad. Okay, so p-value is 0.0073. Now the rule is as it was before, and I feel like I just want to copy. I just kept copying it last week. So there was this rule right here for dealing with p-values and your final conclusion. Okay, so I'm just going to copy and paste that. It's always the same criteria for making a decision. So let's put this in down here. When the p-value is less than alpha, you reject the null hypothesis and support the alternative. Otherwise, if the p-value is bigger than alpha, you don't reject the null hypothesis and you don't support the alternative. So, p-val, according to this, the p-value is 0.0073. Okay, this is less than, I think our alpha was 0.01. It said 1% significance. So when it's less, you reject the null hypothesis and support the alternative. Now remember, the null hypothesis said that the mean mood level is the same before and after Prozac. And we're rejecting that. Okay. Prozac is having an effect according to our data. So when we reject the null hypothesis, we support the alternative, H1, which says that mu1 is less than mu2, which again is saying that the mood level on average is lower before Prozac and higher afterward. Okay, any questions about that? And then you need to say that in sort of a plain language conclusion. So let's go ahead and write that out. The data support the claim that, I'm just going to say Prozac is effective in elevating mood on average. And Prozac's just a funny drug. And from what I hear, it's not that effective. That for many people, it doesn't do a thing. But there is a group that are helped by it. It just depends on who you are. So on the p-value less than alpha, is it less than or equal? Well, Susan, I don't care. I could go either way. Look, I just erased it. So you're not going to end up with any ties, because the thing is with the p-value, you always have several places after the decimal, and the alpha is always only 2 places after the decimal. It's just, they're not going to be the same number. Okay, so I think it's okay to just say less, though. Some of the books are starting to say less than or equal, so it's just a matter of which book you're reading. And I think in my book, I always say less than. So thank you for pointing that out. You got me. How dare you? All right, so that's the end of that lesson. I'm just going to go ahead and zoom out and recover from all my problems that I've had today in my short break. And let's go ahead and try and get back at 10:05.